Assalamualaikum and hello, doctor. We are from Group 1. We will be presenting about applying object-oriented metrics to assess software quality, a case study on Apache command line using CK metrics and SonarQube. So these are the article that we actually refer. So you can click there to see the full version of it. Yeah, we will be sharing about the summary of the selected article later on. So here are the group members: me, Udina, Shahidatul, Mahmud, and also Akil.
My name is Mahmoud Musa Osman with the matric number 290863. I'll be talking about the article information we chose in our project. For this project, we selected an academic article titled Metric for Measuring the Quality of Object-Oriented Software by, by Gandik Sai, published in 2013 in the ACM Digital Library. The paper uses a case study approach to evaluate software quality using object-oriented metrics. The main objectives of the article is to measure software quality across multiple versions using object-oriented metrics and to analyze how software quality changes over time. It also aims to identify early sign of quality degradation and to validate the effectiveness of the CK metric as quality indicators. In terms of methodology, the original study analyzed an open source Java system across multiple versions. The researchers applied CK object oriented metrics, collected metric value for each version, and then analyze analyze the trends using charts and graph. This article forms the foundation of our project because it provides a clear research methodology that we can adapt and apply to a real software system. Moving on to our own project, the work we did based on trying to check if we get the same output from if we get the same output with the selected article we chose, and we were able to successfully get that. We adapted the methodology from the article and applied it to apt.coms lang, which is an open source Java library. We selected this system because it is actively maintained. It have multiple versions available. It is suitable for object oriented metric analysis. Our main objective was to apply CK metrics together with SonarQube and observe software quality trends across different versions of the system. For the tools we use SonarQube, which was being run from Docker and all, to analyze code quality issues such as maintainability, bugs, and code smells, which we also use the CK metric tools to extract object-oriented metrics like CBO, LCOM, RFC, DIT, NOC, and WMC. Then GitHub was used for source code access and version management, and Docker was used to run the SonarQube locally. The object-oriented metric analyzed include the lines of code, which is LOCB. Then there's more of CBO, LCOM, RFC, WMC, DIT, NOC, and the MI, which is maintainability index, which we then use to analyze software quality trends based on the different version. In this demo, I'll show how I use Docker to run SonarQube locally and analyze multiple versions of the apt.coms language using object-oriented metrics. I'll start by showing the Docker container, then the SonarQube dashboard, and finally the terminal execution. So yeah, I don't want to restart the system because when you restart the system, it's gonna take so long, like 5 minutes, and it's taking up all the time of my presentation. But let's say there's a place I want to show you how I get to gracefully stop the workers and restart it again because it took quite a long time. Yes, this is the place. Stopping Sonar Cube. When I stopped it around 8:50, then yeah, stopping the computer in English. SonarQube has been gracefully stopping the worker. And when I restart it again, it's kind of take load, it install, deploy, load plugins and all until when it reaches there, the process of SonarQube is operational. So now I'll move to the web page. The SonarQube is starting. So let's say I reload. Try again. So it's loading, login to SonarQube. So because initially when you started it will be login admin, password admin. So they'll force you to change the password. So for now I've changed the password and my still login is admin. So login. So this is how the dashboard look like. Sorry for the delay, the internet is kind of slow. Yeah. So you get to see all the metrics of different apt.coms language version. This like the project page. Then the language versions from 2.0 until 3.9. Then all the status, it's all passed with the bugs, vulnerabilities, code smells, and the lines of the code all in total, and you get to see the issues, like the issues of each version and all. Okay. Yeah. Yeah. For this issue, you can go here. The type of bug, the vulnerability and all. Code smell is like 9,000 for the code smell. So this SonarCube web interface is only on my local host, and each project represents a different version of Abscom language analyzed separately. So let's say, for example, let's click this project. Here's the overview, the 12 bulbs, it has 12 bulbs, the code smells, which are 856 or so. So the one only indicates a newer version exists. It does not affect analysis result actually. So this is like an older version, which is the 2.0. Then yeah, I think for now that's all for this.
Alright, so for adaptive methodology, there are 7 phases in total. So for this first one is that the software selection. In the article, they use JFeature while we are using the Apache Commons Launch because it is an open source system to study. And for the second phase is that the version selection. They are choosing 11 versions. So we are also downloading the 11 version in the website. And the third one is that the metric selection. They are measuring the 9 CK metrics in order to measure code quality. For the fourth one is that the data collection. Because it is not mentioned explicitly in the article, we merge all the metrics because we use 2 tools, which is the SonarCubes and also the CK, and we export the data set in order to do the data analysis by having trends and also quality changes and identified across the versions, and then we do the visualization by plotting all the data and also build a dashboard in order to view the overview. And the last one is that we do the interpretation, which is we explain all the results and evaluate the software quality evolution. Alright, so next, since the paper did not specify any tools that we are using, so we are using like 6 main tools over here. So SonarCube and SonarCube Scanner are working together to run the source code analysis and calculate the quality metrics. But then we will realize that the SonarCube has some limitations, so that's why we are combining with the CK tools that calculate the rest of the quality metrics so that we can duplicate the paper. And then for the Python, we are using it for the automation and also the data processing that we can see in our GitHub repository. And Java Maven required to use for the run and also manage CK tools.
My name is Irdina. Number matrix 295286. I will be sharing about results and analysis that we gain for this method that we implemented from the research paper. Okay, so we successfully collected metrics for all 11 versions of Apache Commons Lang. The following table represents the complete datasets, which involves tools that we use, SQ, SonarCube, and also CK2, which is the Shidember and Camera metrics implementation. Yeah, so SonarCube did offer industry standard maintainability and complexity measurement. Yeah. For CK2, we use to calculate CBO, LCOM, RFC, WMC, and OC, DIT, while for SonarCube, we use for LOC, MI, and also CC. Here shown the statistical summary for each of the metrics there. So we can see that in each version that we did test it on, which version is the minimum that shows the minimum calculation, the maximum, and also the average, and what is the trend that we receive through each of the phase, through each of the version. Yes. Okay, here the trend for lines of code metric. Overall, it shows 148.7% increase from version 2.0 to version 3.9. Yeah, the increasing of LOC trend indicates continuous feature addition and code expansion. The slight decrease at version 3.0 suggests code cleanup and refactoring during the major version transition. While for cyclomatic complexity, overall it shows decreasing trend from 2.76 to 2.53, which calculated to 8.3% reduction. The decreasing CC trend is positive, indicating that despite code growth, the average complexity per method or class has decreased. This suggests good code quality practices such as method decomposition and complexity management. Okay, for coupling between objects, overall it shows increase of 18.6% from 2.63 to 3.07 version. Interpretation, the increasing CBO trend indicates growing into dependencies between classes. While the values remain relatively low, below 4, the trend suggests increasing coupling, which may impact maintainability and testability. For lack of cohesion of methods, overally it shows increasing of 59.6% from 239.35 to 382.00. The increasing in LCOM trend indicates decreasing class cohesion over time. Higher LCM values suggest that classes may be performing multiple unrelated responsibilities, which violates the single responsibility principle. This is a quality concern that may require refactoring. Overall, it shows 3.4% decrease from 12.41 to 11.99, but peak was 15.14 at version 2.6. So the RFC trend shows an interesting pattern. Actually, initially increase, followed by decrease in recent version. The decrease is in recent version is positive, suggesting improved method organization and reduced complexity. Overall here it shows decrease of 22% from 39.33 to 30.69. Peak was at 46.55 at version 2.6. So the decreasing here, it shows that in recent versions is positive, indicating that classes are become less complex despite code growth. The significant reduction at version 3.0 reflects effective refactoring efforts that simplified class structures. Overall, it shows 20% decrease from 0.20 to 0.16. Peak was 0.28 at version 2.2 and version 2.3. So the decreasing of NOC trend suggests reduced use of inheritance hierarchies, while lower NOC can indicate less reuse. It may also reflect a preference for composition over inheritance, which is often considered a better design practice. In this depth of inheritance tree metric analysis, overall it shows 10.8% decrease from 1.66 to 1.48. Peak was at 1.07 there at version 2.2 and version 2.6. So the decreasing DIT trend is positive, indicating shallower inheritance hierarchy. Deeper inheritance can make code harder to understand and maintain. So reduction at version 3.0 aligns with the refactoring effort that simplified the class structure from the previous analysis. For maintainability index, overall it shows 5.4% increase from 109 to 115. So the increase here, it's actually highly positive, indicating improving maintainability despite code growth. This suggests that the development team has maintained good practices. Maybe they did code documentation, low technical debt, or manageable complexity. So yeah, the jump at version 3.0 likely reflects the benefits of the major refactoring effort. Okay, this is the comprehensive dashboard of each of the graph that we have seen before, including each of the metrics. So yeah, we can see that the transition from Common Slang to Common Slang 3, version 3.0 shows positive impact, which also can consider that they have improved maintainability index, better complexity management, and also they did a quick clean up a bit, temporarily also decreased that. So yeah, that's overall of it. Thank you. I'll pass to the next presenter.
Hi, Assalamualaikum. My name is Muhammad Akhil. My bin Fahmi Azim. My metric number is 3079117. So I'm going to explain about comparison with the original article. So first one is the overview comparison. So first, the aspect that we compare is software. The original studies use the Jeffrey chart compared to us Apache Common Slangs. And they use the multiple versions of Analyze, and we have used the 11 version 2.0 till 3.9. And then we use the same metric Analyze, which is 9 metric that we discussed before. And then for the overall quality trends, the original study shows a declining trend, which has 8 metric increasing and MI decreasing. For us, we have the 6. We have a mix trends, which has 6 improving and 3 metric constant. So here for the summary of comparison tables, we have two tools, which is CK tool and SonarQube. And here's for the table, we have a few pattern which have the similar agreement, which is LOC, CBO, and SCOM. And we have the opposite agreement, the pattern of increasing on JFree charts and decreasing on Apache Common Lang for the CC, FRFC, and WMC. For the continuous of the summary comparison table, so this is the rest. For the same trend, both NOC and DIT showing the same trend of JFree chart is increasing and Apache Common Slang is decreasing, which is opposite in the agreement. So and the last one, MI, which shows the JFree chart decreasing and Apache Common Slang is increasing, which is in the opposite agreement. If you want to know more about these details in the table, you can see the GitHub. As for critical analysis of preferences, for software project, we have Jeffrey charts. We have it is more complex visualization logics. And for Apache Command Lang, we have simpler and more focused functionality. For development practice, we have Apache Command Lang tends to have better code quality practices, code reviews, and refactoring process. For the project lifecycle stages, Every version analyzed may have represent different maturity stage. Our common lungs transition to version 3 represent a major quality improvement efforts. So lastly, the two differences. Different tools may calculate metrics slightly differently. However, both studies use the industry standard tools, such as CK metric suits. So the implication is the software quality is not predetermined, active quality management matters, and refactoring is effective. And the last one, metrics are project specific.
So over here, I will present about the what original paper doesn't have, but we are doing the extended analysis because we are using the SonarQube. So like there are so a lot of valuable insights that can be used in order to measure the software quality. So for example, like security, they are giving security ratings like A, B, C, and then reliability rating, and also there are code smells, duplication, code coverage analysis, and these are also useful. And I'm going to demo in the next slide. So just making sure it's running. So over here we have the 11 versions of Apache Commons Lungs. So we have a box over here. We have the vulnerabilities, code smells, and then also the duplications and also the lines. And at the left side we have the quality gates. 11 version is fast, reliability, security review, and also the duplication, all the informations that gonna be useful for our project. And this one is issue combining in the 11 versions got code smells that indicates the deeper problem in the structure. For the quality gates, we can see the coverage is 80%. And then also we got the reliability ratings, reliability reviews 100%, and no vulnerabilities. Okay, so let's go to each of the project. We're going to go to the 2.0. So let's go to the measures that have not been covered in the article. So over here we have the security, reliability, and also we can go to the coverage. So let's just click this one, overview this graph, and then also the duplication. You can see the number of duplication. We got 1,400 more. So if we're combining all the information, extracting all the information for the SonarQube, and then put it in the table so that it can be more readable for the user.
As for conclusion, throughout applying SQA research methodology, we were able to connect the theory of practice in order to understand real-world SQA research designs by utilizing tools, methods, metrics to analyze or improve the software quality. Our three key findings that we got is the positive quality indicators, concerning quality indicators, and lastly, the version transition impact. And the other things is the methodology effectiveness. The evidence that it links specific metrics to quality attributes, such as cyclomatic complexity to code complexity, maintainability index to maintainability, coupling between object to class interdependencies, and lastly, the lack of cohesion of methods to class design quality. And lastly, for the recommendations, we have the two practical recommendation and feature improvement. So the suggestion as below is to address increasing coupling, is CBO, improve class cohesion, LCOM, manage code growth, LOC, and maintain the positive strengths, adopt the test-driven development, TDD, and implement the continuous quality monitoring. As for the feature improvement, we can define acceptable metric range, expand case studies, explore AI-powered quality predictions, integrate additional metrics, and longitudinal studies.